Hi, this is Yara Ghamloush. Welcome to my poster. I'm going to first introduce to you the main idea behind my research, and that is combination sensitivity. So combination sensitive neurons exist in our brain. They are extensively studied in the inferior colliculus of bats and frogs, and they are also studied in the motor nucleus of songbird, called the HVC nucleus, which is the equivalent to the mammalian motor cortex. They have the property that they respond not only to one stimuli, but rather to a combination of stimuli presented together. So in my research, I focus on this behavior in songbirds, and here you see a sagittal brain slice of a zebra finch bird, and I zoomed in on the HVC area, which is the hub of combination-sensitive neurons. This area has three classes of neurons: the forebrain projecting, called RA projectors neurons, and the basal ganglia projecting, called X projectors, and the interneurons. So in order to see this behavior in songbirds, we record from a combination-sensitive neuron in a living bird while presenting to it a certain syllable that is part of its own song, call it syllable A, and we see that this neuron remains silent. And if we present B, the neuron will also remain silent. But if we present A and B afterwards, the neuron will spike. And if we present B first and then A, the neuron will not spike. It will stay silent. So in order to understand this combination sensitivity behavior, we need to understand the network that it is embedded in. And therefore, in my work, I try to design different scenarios that connect these three classes of HVC exoneurons in a realistic Hodgkin and Huxley model of neurons using pharmacologically identified ionic currents and pharmacologically accurate synaptic currents. Here I present you two circuits which we came up with that render this behavior possible. And I'm illustrating the dynamics of circuit one when I present it with A and then B. So the first syllable A is presented, the A-selective neuron fires, and then interneuron 1 will fire due to the excitatory coupling between interneuron 1 and the A-selective neuron. And in its turn, X1 will be inhibited due to the inhibitory coupling, but it will then do a rebound burst when A has finished. And this will happen at the same time that B has been presented, and therefore the B-selective neuron will fire. Afterwards, interneuron 3 and X2 will fire, but interneuron 2 will not be able to fire due to the inhibitory input from interneuron 3, and therefore our combination selective neuron will be only receiving an excitatory input from X2, which will make it fire. If you would like to know how this goes for presenting A, B, or B, then A scenarios, and for the circuit 2 diagram, please join my discussion and download my poster. Thank you for watching.